Okay, hi everybody. It's time for week 2 at Rasmussen College. This is Chemistry 1100C, Section 12 with Dr. B, and here's what we'll be talking about tonight. Let's review week 1, see what we learned, what we struggled with. Let's look at the new topics for week 2. Let's talk about the assignments for week 2. And let's see what's coming up the following week. And at about that point, I'll include the magic words so you can get credit for watching this. Okay, what we learned week 1. This topic was matter and measurement. We mixed chemicals in a virtual sense. We looked at significant figures. We looked at adding and subtracting numbers. We took a look at data. And some common errors were administrative in nature. Some people struggled to submit their documents on Blackboard, so I'm including this How to Submit an Assignment YouTube video. You can go ahead and click on that. I will include this slideshow. You could also just Google how to submit an assignment in Blackboard. It's the first thing that shows up. I found it very helpful. Most people manage to figure out how to do it. A friendly request, submit what is asked for. If it asks for a Word document, give me a Word document. If it asks for an Excel spreadsheet, please give me an Excel spreadsheet. There you go. The most common issue with the assignments were excessive numbers of significant figures in problems, which is very common on any level of chemistry. Let's solve a problem and do it right. Suppose you were given a chunk of aluminum. Its density is 2.7 grams per mil. You stick it on a scale, you find that it's 2.45628 grams. The question is, what is the volume? Well, I'll bet you could set it up. You could convert from density given a mass and volume. I'll show that. But and you could get a raw number by punching it in. But the question is, how many numbers should we include? The mass is ridiculously precise. The density is not so. Significant figures are set up so that you never get better than your worst number. After all, if this was 2.7499, something like that, it would still come in at 2.7, but it would be much closer to 3 grams. Its volume will be less, actually, if its density is very high. And so you have a lot of uncertainty in this number. So let's punch it in. I did it by unit conversion. 1 mil for every 2.7 grams. Notice I had to flip that over because I know in the end I need the volume in milliliters. And if 2.7 grams comprises a milliliter, it's just as accurate to say that a milliliter is comprised of 2.7 grams. Enter that and you'll see that we have mils over grams times grams. That means grams over grams cancels and we get 0.9099. That should be mils. I think I wrote it as mils here. Yes. So include your number to the correct number of significant figures. In this case, 2. Because when you're adding and subtracting, it's a different rule. However, when you're multiplying and dividing, the rule is to keep the lowest number of significant figures, which is 2. So we have a number to the correct significant figures. We have a unit, which is milliliters. Change that to milliliters, please. And if it said aluminum, that would be called the label. We'd include that as well. 2SF means 2 significant figures. For this week, we'll be studying atoms and molecules. I have 4 slides I'm going to show about that. For the assignments for week 2, I will give some assistance at the very end of this presentation for the first lab, which I thought was a pretty good question on calorimetry. We'll talk about the Powerade lab, the periodic table lab, the first assignment, and the quiz. When I go over the topics for week 2, they will be specific to assignment 1. Everything you need to know about assignment 1 will be in here. Taking a peek at the quiz, I found there's additional material you'll need to learn, so I've listed the additional topics so that we have a nice focused review here, and you should be in good stead there. Now, last week I went through the nitty-gritty of how to set up your online virtual lab and get it rolling. This time I'm not going to talk as much about the actual moving flasks around and insulating them, things like that. I'll let you sweat your way through that. Hopefully you're a little better at it now. What I will do is I will help you with the first calculation for Lab 1 coffee. I like that calculation. Okay, coming up next week, it'll be time for bonding, compounds, and formulas. You'll see a lot of overlap. It's really hard to talk about atoms and molecules in a real sense without including some of these topics. I'll include the magic word at that point, and I will give you some advice on the coffee lab. Here's where we are overall. It's a 5.5-week course. We've completed the first week. We are now into the second week here. 3 labs, a quiz, an assignment, participate in the live classroom, get your 230 points. Here it is in one big page what we're doing for week number 2. Here's some details about what we'll be learning about atoms and molecules. Here's the pacing schedule. I would suggest you spend 2 days doing the extensive reading and activities. None of these have point value, but checking the quiz, I found that a lot of these topics were included. Last week, you might have noticed that the quiz didn't really go beyond the assignment. This time it does, so at least check out the additional topics that you should learn to make sure you do well on that quiz. I would recommend getting into the labs by Wednesday. Listen to the live classroom presentation at 7 p.m. And then let's get the labs wrapped up by Thursday, do the other 2. I believe that mostly they just call for taking a picture of it when it's done, including your calculations. They might be a little easier. You let me know what you think. On Friday, that's a good day to get that assignment done. I would also, although it's not written, I would review for the quiz because it's kind of a toughie, and then take the quiz on Saturday. Be sure to post a discussion reply on Sunday or use that full day just to rest, and you'll be A-okay. Here's where all your points will come from this week. Here's the big points, and here are the scoring rubrics for everything. So if you're wondering about the details where the points come from, they are right there. If everything goes well, here's what you'll be saying to yourself during week 2. Monday went well. I reviewed all those foundational assignments. I did my reading. I took a look at that. On Tuesday, I posted some stuff to the discussion board. I took a look at some of these activities that don't have point value, but I learned from them. On Wednesday, I completed labs 1 and 2. That's the coffee lab and the Powerade lab. On Thursday, I finished the last lab, which is the periodic table, and all I got to do is the assignment and the quiz at this point. I did the assignment on Friday. I started reviewing for that quiz using the additional topics listed by Dr. B. Saturday, I took the quiz. I did amazingly well. And Sunday, I rested. That's a really good suggested pacing chart. Okay, let's talk about a few of the topics: atoms, molecules, and additional material. After that, there's 3 or 4 slides I need to cover here. Okay, here's the topics we'll cover about the atom, so let's go ahead and dive right in. You could always watch this a second time. I've tried to set this up so it's sort of flashcard-like. I'll try to put these in the form of a question so that this can help you learn on the fly. What's everything made of? These little spheres. Yes, these are atoms, the building blocks of nature. Tell me about those 3 subatomic particles. Well, you got your protons and your neutrons inside the nucleus, and you've got your electrons outside the nucleus in shells. First shell can hold 2, second can hold 8, etc. Protons are attracted to electrons, and to designate that, we give them opposite charges. We call this model that you see there the Bohr model of the atom. On the actual quiz at the end, you should be responsible for knowing some of the historical achievements that led to this model. This particular atom we're showing has 8 of each of the subatomic particles: protons, neutrons, and electrons. Let's name it. We can name the identity of the atom by just counting the number of protons. This is known as the atomic number, and that number is absolutely specific for an element name. In this case, we have 8 of them, so that element name must be oxygen and its symbol must be O. Quick pet peeve, it's always capital letter, then small letter if it's a 2-letter system, and most of them are. It's not capital C, capital L for chlorine, for example. Now, the number of neutrons is a little bit funky. It can vary within the element. So you might have an atom of oxygen that has 8 neutrons, like this one. You might have another atom that's still oxygen that has, say, 10 neutrons. These are known as isotopes. Same element, different number of neutrons. This will lead to different masses for different elements, which we'll have to account for. There's another number that gets confused sometimes with atomic number. It's called mass number. It is protons plus neutrons. I'll say the words and tell me if that makes sense to you. Mass number minus atomic number equals number of neutrons. That should make sense. Protons plus neutrons minus protons equals neutrons. It's another way of saying that the mass number kind of hides the number of neutrons within it. We can designate this particular atom using dash notation to tell us everything about p's, n's, and e's. This has the designation O-16. Let's make sure we understand that. The O means that it must have 8 protons. The dash is just a dash, it's not a negative sign. There would be a charge right there if the number of protons did not equal the number of electrons, but it does. We are 8 plus, we're 8 minus, there is no charge. Keep your eyes open for a little charge right there. 16, because we always put the mass number there. And if you're thinking deeply, this means that we have that flavor or isotope of oxygen that has the 8 protons there. Here's one for you. Oh, and before I do that, the quiz also expects you to understand this in terms of what they call box number. I didn't put it on this slide, but I will walk you through it. It's quite similar. Instead of calling it O16, we put an 8 down at the bottom there, meaning that it's oxygen. It's a little redundant. The oxygen has to have those 8 protons. It'll always be 8 there, and then you'll see the 16 on top. So atomic number on the bottom, mass number on top, and they skip all this stuff. Occasionally they do put the charge right there. So I'll answer this one both for box notation and dash notation. If it's 11 protons, I guess it's sodium. Let's give it an Na, followed by a dash. Does it have a charge? In fact, it does. It is 11 in the plus, 10 in the minus, therefore it's plus 1. Mass number is 23, that's 11 plus 12. So that is the dash notation for the sodium cation here, that has 12 neutrons. The box notation, I'll sort of walk you through it. Write your Na, write your plus, even though I'm not writing anything there. Put your 11 on the bottom, put your 23 on the top, on the left, and you got yourself your box notation. Since isotopes exist, meaning atoms of the same element have varying masses, what a pain. The periodic table solves this by writing the average atomic mass for each one of these. Take a look at, for example, chlorine. You'll see that it's about 35.5. Now there's 2 isotopes. One has 18 neutrons, one has 20. And 18 gives you a mass number of 35. 20 gives you a mass number of 37. Most of it is the lighter variety. In fact, 75% of it is the chlorine 35 isotope. Can you see that we are much closer to 35 than 37? That's called ballparking your answer, and it's always a good idea. To solve it explicitly, convert those percentages into what's known as abundances. That means just express it as a decimal. 75%, you write 0.75. And just follow yourself through the words is what I do, and you always get the right answer. 75% weighs 35 and 25% weighs 37. This will give you a weighted average. Apply your PEMDAS, your correct order of operations, meaning turn that into a number first, write it down. Turn that into a number second, write it down. Add that number to that number, and you should get an average atomic mass of 35.5. The common units are AMUs, atomic mass units. Okay, next topic is the periodic table. We're going to talk about valence electrons, noble gases, common ions, and the electron configuration. There is a little bit about the history you'll be responsible for on the quiz, so I recommend you do that reading. This gentleman here is Dmitry Mendeleev. I hope you get to read about him and his adventures. He's sometimes referred to as the father of the periodic table. And here's what they came up with as it exists now in its modern day. A good place to start is just number them by protons, right? Since number of protons defines the element, and there's currently 118, let's just make it look like a book, 1 through 118. Notice 19, 20, 21, 22, da, 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 da. Largely, we're just reading it like a book ending at 118. Let's give it better organization, and very important organization in terms of the columns. And for these, it's organized by what's known as valence electrons. Everyone in this group has one outer shell electron. This particular atom you see here has 6 outer shell electrons. You may recall we defined this as oxygen. There it is, valence electron 6, and it's right there. It goes like this, 1, 2, All of these are 2. 3, 4, 5, 6, 7, 8. That's very important because that number of valence electrons determines its chemical behavior. So you get all of these atoms tend to be flammable metals. All of these atoms tend to be inert, things like that. So it's a nice handy ways to organize it primarily by column. Make sure we got everything here. Valence electrons, check. Let's look at a few other things. Noble gases. There's a few common groups here, and that's what they call these columns, groups. For example, alkali metals, alkaline earths, halogens, and these are the noble gases. The noble gases are a great thing to take a quick look at because they're completely unreactive. They don't do anything. And if you take any one of these elements and you add or subtract enough electrons to make it have a full outer shell, just like the noble gases do, they get greatly stable also. Of course, they have to have a counter ion that goes with them, but they become very stable compounds. What I'm saying is that, see these group here? They all have this group, the alkali metals, all tend to lose 1 valence electron. Why? They want a full outer shell. They could gain 7, but that's ridiculous. If they lose 1, it reveals the full outer shell underneath. So these all tend to lose 1 and form the common ion, the all plus 1. These are group 2, so they'll lose plus 2. Skip over this for now. These are plus 3. They'll lose all 3. These will either gain or lose 4 because they want a full outer shell, which is typically 8, so they're right on the cusp. However, once you get 5 valence electrons, it's easier to gain 3 than to lose 5, so these will form minus 3 anions. Don't let those minus signs put you off. Just remember that electrons have negative charges, and so if you have more of them, you have more of a negative charge. These have 3 extra electrons, is what they prefer to do. Minus 2 for the oxides, gaining 1 for the halides, and the noble gases do nothing at all. We do also have to mention electron configuration. This is a way to assign numbers and letters to each one of these that gives you some useful information. There's a lot more to it than that, but this will be the brief way of doing it. Let's begin by dividing the periodic table into little blocks. First 2 columns we'll call the S block. We'll also delineate each shell by the number here, right? So we're in the 4th shell here, we're in the 7th shell here. This is the 1st shell, that's the 2nd shell. We'll call this block the D block, this one the P block, that one the F block, and let me say something quick about the F block. It doesn't really belong there. Can you see how we skipped from 56 to 71? The missing pieces are there. They belong right in between there. Similarly, this row should be right here. It's only placed there to alter the shape so it's more like, I don't know, a piece of paper. Now, if you have these S's and P's and T's and F's, if we read this entire periodic table like a book, we should be able to designate every single element in that manner. 1s1 for hydrogen, 1st shell, S-shaped orbital, we'll say, for the electrons. I don't want to get into that too deep. This one, since the 1st shell only requires 2 electrons, is also an s orbital. It's kind of an exception. Sorry about that. So we're at 1s2 to start off. 2s2, meaning beryllium has an electron configuration of 1s2, 2s2. Then we proceed on through 2p6. The complete electron configuration of neon is 1s2, 2s2, 2p6. It ends in 2p6. Fluorine is 1s2, 2s2, 2p5. This will actually reveal where all the electrons are in detail. I'm going to go right to the end, 118, and watch me list this series here without memorizing it. Maybe you can tag along and do it at the same time. 1s2. 2s2. Here we are. 2p6, 3s2, 3p6, 4s2, 3d. It slips back down to the 3rd shell. 3d10, 4p6, 5s2, 4d10, 5p6. These little things here help you a lot. 6s2, but we're at 56, so we have to go to 57. So after 6s2 comes 4f14, back up to 5d, 5d10, 6p6. All I'm doing is going from 1 to 118. 7s2, 5f14, 6d10, 7p6. This is the electron configuration of oganesson. little bit about molecules and compounds. We'll get some formulas from the names. We'll come up with mass ratios and atomic ratios. Most elements are unstable. That being the case, they form molecules and compounds. Very similar words. Molecules tend to be used for individual molecules that are not part of a big lattice. That's usually the molecules that form from atoms that are to the right of that staircase, non-metals. Compounds tend to have a continuous lattice of positive and negative charges that exist in 3 dimensions. Harder to see the individual substances that comprise them, and ionic compounds oftentimes use that word. It's not that big a deal, but that's the difference. You may recall that ions come from substances that are not noble gases. If they only have a couple or a few valence electrons, they'll tend to lose them to form cations. The ones on the right tend to gain them to form anions. They are then oppositely charged. They will be attracted to each other. They will make ionic compounds, also known as salts. So if we had a sodium cation, it would be attracted to a chloride anion. Have your periodic table out, pause if you need to, and you'll notice that these charges are valid. In other words, atomic number 11 is sodium. Find it at the top of the periodic table. You'll see a +1. And it will tend to form sodium chloride, table salt. Now, they write it as Na1 plus 1 initially, but chemists have said, why don't we just drop that if it's 1? So they just call it NaCl, sodium chloride. Now, when potassium combines with oxygen, it won't do so in a 1-to-1 manner. Potassium tends to lose 1 electron. Convince yourself that's true on your periodic table. Oxygen tends to gain 2, so Ko would be a -1 charged substance. But if it's K2O, it isn't. The 2 plus 1s will offset the -2. So these sort of auto-combine so that they become uncharged, giving us potassium oxide with a molecular formula of K2O1, which we drop the 1 and we call it K2O. So what would calcium chloride look like? Can you see that it would be CaCl2? What would aluminum oxide look like? Can you see that it would be Al2O3? I hope you see that. Are you noticing this drop and switch pattern? 2 goes there, 1 goes there. 3 goes there, 2 goes there. Check it. The 2 plus 3s total +6. The 3 minus 2s total -6. It's uncharged as it must be. A little bit about some molecules that form, and these are things that are to the right of the staircase. It's not an electrostatic attraction, but a different type of bond. We'll learn later it's called a covalent bond. But I do just want to mention that if you have substances that contain hydrogen, oxygen, nitrogen, or carbon, they follow a very predictable bonding pattern. Hydrogen tends to form 1 bond, oxygen 2, nitrogen 3, carbon 4. Honk if you love chemistry. Do you see that mnemonic? And if bonds are lines, and they are, there's only one way we can draw water. Can you see how oxygen has its 2 bonds? Hydrogen has its 1 bond. No other combination will fit. Similarly, carbon dioxide. Now there you might say, boy, carbon forms 4 bonds, oxygen's 2. Always put the highest bonding atom in the center. That would be carbon. But you might not see how to get there. You got to use double bonds. See that? 2, 4. Ha ha. Oxygen, each one has 2. Good to go. Try drawing H2O2. This is hydrogen peroxide. Notice it's not water. And there's only one way to do it. The oxygens form the largest number of bonds at 2, so put them in the center. They both have 2. Put your hydrogens at the periphery because they only form 1 bond, and you are good to go. So now we know how to write some compounds and some molecules. Let's name them. You already know how to do this partially. NaCl. Is that not table salt sodium chloride? It is. CO, toxic gas. You may know its name. It's carbon monoxide. Lo and behold, we've learned something. If it's to the right of the staircase, this is not a salt. Both carbon and oxygen are nonmetals. Use those monoditris, right? Carbon dioxide, things like that. But if it's a salt, we don't say sodium monochloride. It just sounds funny. So, ionic, don't use monoditri, but to the right of the staircase, always do. Apply that to AlCl3. Yeah, it's a salt, aluminum chloride. This one's not. Everything's to the right of the staircase. Sulfur dioxide. New rule, if you're in the D block, I have tried to avoid talking about it because it doesn't follow the rules as much for reasons I don't think we'll go into at all. That iron can form different charges. In this particular case, I hope you can see that it has to be +4. Each oxide's -2, totaling up -4. The iron must be +4 to offset it. Since this substance is, as they say, polyvalent, the D blocks can be +2, +3, maybe even +1. We specify the charge with a Roman numeral. This is iron 4 oxide. Try to name this one, and you'll see this is a covalent right of the staircase gizmo. We'll just call it silicon dioxide. Finally, atomic and gram ratios. The atomic ratios are all over the place here, and they're very easy. 2 to 3 for aluminum oxide, 1 to 3 for aluminum chloride, 1 to 2 for iron 4 oxide. So that's pretty straightforward. Water is H to O ratio of 2 to 1. Beware of those cases where you can reduce it down. It's best to say that hydrogen peroxide has an H to O ratio of 1 to 1, not 2 to 2. Now, the average atomic masses will define the mass ratios. Life would be simple if all atoms were the same size and the same mass. They're not. The small ones, like hydrogen, are the lightest. The big ones, like moving towards organescent, are the heaviest. So if we have a ratio of 1 to 3 nitrogen for every 1 nitrogen atom for every 3 hydrogen atoms, that does not mean we have 1 gram of nitrogen for every 3 grams of hydrogen. If you look up the average atomic masses on a periodic table, that's the number with the decimal places. You'll see that each nitrogen is 14 times heavier than a hydrogen atom. So even though we have 3 hydrogen atoms, the ratio will be 14 to 3. That's 4.67 to 1, and that would be the mass ratio of this substance, which is ammonia, present in Windex, for example. That means ammonia always has 4.67 grams of nitrogen for every gram of hydrogen. Okay, I did want to throw in one little assistance slide. I just went ahead and solved the problem for the coffee lab. Now, you'll have to sweat your way through the online lab, getting your flasks and your calorimeter and things like that, and insulating everything. Note there's some very helpful hints within Blackboard. But here's the question, and I want to offer a few hints in case you're struggling with it. It's a classic problem that most chemists have to solve sooner or later. This question has been applied to coffee, which I kind of like. So how much cold milk, that's 5-degree milk, has to be added to a nice big cup of coffee, 250 mils, that's already very hot, it's at 85 degrees Celsius, but we want to add just enough milk to bring it down to 70. And we want to calculate it, not do it. I mean, it would be pretty easy just to pour in the milk and stop when it hits 70, but we can calculate how much cooler it has to get. Here's the idea. Certainly adding cold milk to hot coffee will cool it down. And we need to cool down the coffee by 15 degrees. Can you see that? Delta T is 15 degrees. Let's assume it has a similar specific heat of water at 4.184 joules per gram degree Celsius. Let's assume its density is very close to that of water at 1 gram per mil. We can then use Q equals mc delta T to see how many joules of heat need to be removed from that system to cool it down. I like to use these subscripts to remind me of what I'm dealing with. I am not dealing with milk at all, so I'm going to use subscript C for coffee. This literally says that the amount of heat that has to be removed from the coffee is equal to the mass of the coffee, which is given, kind of, you just have to convert from milliliters to grams, times the specific heat of coffee, which we'll assume is the same as water, times the change in temperature of coffee, which is 15 degrees. How are we going to remove that much heat? By adding cold water. How much energy in the cold water has to be absorbed, right? I'm saying the milk. The milk's going to get warmer. It has to absorb exactly that amount of heat. So this is the really important sort of pass-through that makes it solvable. The amount of heat that is lost by the coffee is gained by the cold. W I wrote. I should have wrote M for milk. Yeah, here it is, M for milk. I would write M for milk there. Now that you know that number is equal to that number, see this, it will be the same as that. They're opposite values, but don't worry about it because just word it properly. You have to add or this much milk, and that's all you need to know, right? So it'll be equal to the mass of the milk. Now you don't know that. That's what they're asking for, how much milk. Times the specific heat of milk, we'll assume it's just like water, times the change in temperature of the milk. Now, how much warmer does the milk have to get? It started at 5. It has to go up to 70. I'll stop there, and I hope that you can use all that information to find out how much milk needs to be added to your Starbucks coffee. All right, everybody, that covers everything. That took a half an hour. I hope you guys stayed awake, and I'll see you all at 7:30.